In the last class, what we learned are there. I have already written that up. Essentially, that if you have some operator given in the 1, 2, 3, say some operator is there, say omega, in some arbitrary basis, and then you can change the basis by defining an unitary operator like this, and its adjoint will be like that. And in that case, your change vector will be just u operated on the old vector. Any operator will be transformed this way. In that case, it is the adjoint of u, which has to operate on the old operator, and the new matrix element will be given like this. Now, earlier we have learned that if lambda is a Hermitian, then it has orthonormal eigenvectors, right? A Hermitian, then it will be orthonormal or orthogonal eigenvectors, and you can normalize that. So eigenvectors. So if it has orthonormal eigenvectors, then you can very conveniently change the coordinates, change the basis into the basis of the orthonormal eigenvector. Then that will be called the eigenbasis. Eigenbasis. The advantage is that if you can convert that into the eigenbasis, then the matrix will become just a diagonal matrix with the eigenvalues in the diagonal elements. It will be very convenient to work with that kind of matrices, and so we often change depending on what we want to observe. If we want to observe energy, then we express the function in terms of the energy eigenbasis. If we want to observe position, we express it in position eigenbasis. And how to do that, I'll come to that later. If you want to observe momentum, then we express in momentum eigenbasis, and so on and so forth. And it is also possible to convert from one basis to another. So this is something that we have to understand. So for Hermitian operators, we can do this, and that's another thing that we learn. Okay, so let us go ahead with that. One question you might have, if we have two operators, say omega, capital omega an operator, and capital lambda an operator, you know that if these two operators commute, then they have some very significant physical properties. And if they do not commute, they have very significant physical properties related to uncertainty principle. But the question is, now that we are expressing these as matrices, will the matrices will have some property if they commute? So first, let us assume that these are two commuting observables. These are two commuting operators. So commuting Hermitian operators, of course. Otherwise, they will not make any physical sense. I want them to be Hermitian operators. Okay. Then let us start by considering omega to be non-degenerate. So that means the eigenvalues are distinct. So if omega is non-degenerate and we consider an eigenvector omega, so you have omega operator operating on the eigenvector omega I, that will give the eigenvalue times the eigenvector. So eigenvalue times the eigenvector. This is the symbol of a vector. So this is the eigenvector, and this without the ket symbol is a number, that is the eigenvalue. Now we operate the whole thing by this lambda. So you have lambda operating on this whole thing. Will of course give you lambda times this, but this is a number that can be brought forward. So I'll write this first and then lambda omega I. Okay, so it immediately implies, okay, since these two are commuting, so since they commute, I can write this one first and this one then is equal to now notice I have this whole thing and this whole thing here means this whole thing is an eigenvector of omega with omega I as the eigenvalue. So physically what is happening? What is happening is, suppose you have the vector something like this, this omega I eigenvector, and then this lambda omega is essentially stretching this vector so that the omega I is an eigenvector of omega and lambda omega I also an eigenvector of omega, which means that the lambda and omega have a common eigenvector. Now, if that is true for any omega I is just any eigenvector, it essentially means that two commuting Hermitian operators, they have shared eigenvectors. They have common eigenvectors. So this is a very important property that will have some, that means let me write down the conclusion out of this. Conclusion is that omega and the lambda and omega, these two operators have simultaneous eigenvectors. Now, we have already learned that if you define these eigenvectors as the basis, then it will diagonalize the matrix. And therefore, if two operators commute, then they have shared simultaneous eigenvectors. And if you define the coordinates that way, if you define the basis that way, then both of them can be simultaneously diagonalized. So that is the mathematical implication of two operators being commuting. Okay, so let us, yeah, if you have any question, you can ask this now.
So, so what is the why is omega non-degenerate? What is the role of that?
Oh, if you have omega degenerate, then there would be two of these. That means the same eigenvalue with different eigenvectors. Okay, that will be a situation where you have a eigen and a sort of an eigenplane which is orthogonal to it. That's the situation. This eigenvalue, this eigenvector and the eigenplane would be shared. But then in this plane, all the vectors, all the vectors are eigenvectors, right? So yes, all the vectors will be eigenvectors of omega, all the vectors will be eigenvectors of lambda. and then you can only say that there exists common eigenvectors, but for omega you can define one set eigenvector, for lambda you can define another set of eigenvectors, and so on and so forth. So you will have there will be possibility of you choosing different eigenvectors, because now you choose the eigenvector. Everything in that particular plane are eigenvectors you choose. But the point is that there exists a common set of eigenvectors. So it is possible then, even then, when they have degeneracy, even then, to define suitable eigenvectors, suitable bases, which will diagonalize them both. Yeah.
Yes, sir.
Is there any other question? Can we go ahead? Okay, let's go ahead. Let me clear this and then let me go ahead. Okay, by the way, while you have done a course on linear algebra, have you learned functions of matrices? Sorry. Functions of operators. So we have learned that A, B, C, D can be operators and they can have certain functions operating on functions. Okay, fine. But can you have functions of operators themselves? For example, if say A is an operator and I say A squared, what does it mean? It means that A operating on whatever functions comes after this twice. Okay. In a similar way, you can define various functions of operators themselves. And since now we have understood that operators can be expressed as matrices, square matrices, my question to you is that, did you learn how to think about functions of matrices? Did you learn that? Can somebody unmute and answer the question? Did you learn that? Can somebody unmute and answer that question?
So if the matrix is a square matrix, then we can define a polynomial of matrix. That matrix
Right.
without any
Exactly. Exactly. That's something you would learn, right? Good. So exactly. So you can define polynomials of matrices because you can define a square, a cube, and all that, repeated application of that matrix, and therefore you can define polynomials of matrices. And since functions can be expressed in terms of polynomials, you can define, for example, since you can define, say, f of x as some number x, some algebraic variable x, you can define it as polynomial expression. In a similar way, you can define polynomials of matrices. So it will be like function of some operator that will then be expressible as n is equal to 0 to infinity an. Now this one, this is nothing but n times application of their operator on alternate operators. Okay, so since they behave in the same way, various things you can do using operators that so far you were doing in terms of algebraic variables. Various things you can do. Only thing you have to be very careful about is that operators might not commute. While if there are a couple of operators, if there is a function of x and y, they would commute, and therefore you can write things assuming that they commute, while you cannot do that for operators. That's the only care that you have to take. Otherwise, operators can be used, since they can be expressed as polynomials. Operators can also be used as algebraic you can do algebraic manipulations using operators. For example, if you have omega, a Hermitian operator, then you can then in its eigenbasis, we have just defined what would be the eigenbasis, its eigenfunctions. If you define in its eigenbasis, then the omega will simply be the eigenvalue 1, eigenvalue 2, eigenvalue 3, and so on and so forth. It will just be a diagonal matrix like this, just zeros. Okay. What will be omega m times m to the power m? It is nothing but then omega multiplied, this matrix multiplied n times. And since this is a diagonal matrix, it will be extremely simple to express this. It is just this. Right. So you can do various things, and then can we define the exponential of a matrix? Can we define this? Yes, we can, because the exponential of a number of a algebraic variable can be expressed as a power series. So it will be n equal to 0 to infinity omega n by n. So since we can express that as a power series, therefore we can define then an exponential of a matrix. And the only thing that one has to be sure of is that this power series converges, and that convergence can be ensured in most cases, and there are theorems to that. I'm not going into that issue. Point is that we can also define an exponential of an operator. We can define exponential of operator. So, and this exponential of an operator, how would that look like as a matrix? I mean, like this. It will be in each position then, it will be n equal to 0 to infinity. It will be omega 1 to the power m by m real, and so on and so forth. Since these are composed of the products of the matrices which themselves are diagonal, then this will also be a diagonal matrix. This might not always happen, remember that. Omega might not always be a diagonal matrix. If it happens to be diagonal matrix because of this character that you have expressed it is in the eigenbasis, then the manipulation of that becomes rather simple. Otherwise, writing this out is not a very big deal, because this is just a matrix, and all you need to do is to multiply matrices. And MATLAB, for example, has the EXPM function. Within bracket, you put the operator here. The EXPM function actually does the exponentiation of the matrix. That means it is already built in. All this would have been built in. I do not know what the equivalent of EXPM in Python is, but there must be something. You can easily find out. We can quickly illustrate one application of the function of operators. The Schrodinger equation.
So may I interrupt you once?
Sure. Yes. Who is it?
Sir, in the previous expression, in e to the power operator 1, in the matrix, it will be m factorial or n factorial?
Just a minute. Let me go. Whatever. It's not going up. I want to go up there. Yes. Where?
So this one, last step. Sir, in the matrix, last matrix.
Yeah, you are right. You are right. It will be this n. Yeah. It will be n here also. Yeah. That's right. So this will be just this one written in every position of this along the diagonal. That's all. Okay. Thank you for correcting me. Any other question? Can we go ahead? Schrodinger equation, as you know, was I H cross del T of psi x and t, and that was the H operator operating on psi x and t. I can bring this one here, so I can delete this from this position, and I can write it as minus I by H cross. I don't want the I to be in the denominator, that's why I wrote it that way. Now, if there is an equation like, say, d psi dt is equal to sir a psi, how do you solve it? You can easily solve it as the way you would solve it as an exponential. We can easily solve this one also in a similar way. X t, it will be e to the power minus I H operator t by H cross psi x initial condition, right? See, the way you'd solve a simple one-dimensional equation like this, you can also solve a an equation like that in the same way. And then this is H is a matrix, and therefore this is an exponent of a matrix. And the psi at the tth instant, that means it is at some later time t, is then expressed in terms of the psi at the initial time times a matrix. Okay, this is a time translation operator. This is an operator. It's a time translation operator. You can see that in this kind of situations, you do need exponentiation of a matrix. So this is one way of solving the time-dependent Schrodinger equation, which is a very simple solution. And all you need to do is to do the exponential of the Hamiltonian matrix. For that, you will need to learn how to express the Hamiltonian as a matrix. We'll learn that slowly. But you can see that this is a direct application of operation of operators. Good. Okay, let's go ahead. Let me clear this. Okay. So far, you have learned that if there is a Hermitian operator that can be expressed in terms of basis, and the basis are the eigen functions of a particular operator. Now, how about position as a basis? Now, position is a continuous variable. And since position is a continuous variable, we need to understand how to express that as a basis. Energy was a discrete variable in any potential function. In any constrained state, energy becomes a discrete, eigenfunctions become discrete eigenfunctions. And if you have discrete eigenfunctions, then you can easily visualize how we are doing what we are so far doing. But now we also have to encounter continuous set of eigenfunctions. How to do that? Or in other words, how to express a function, say f. We have so far expressed as a linear combination of the eigenfunctions. But now, if these eigenfunctions are continuous ones, then how do we do that? So let's try to figure out visually. I'll do it using this. I'll do it visually by actually plotting a function and say this is my function. How do I express that function? How do I write out this function? This is where we have plotted the function. How do I write it? In order to write it, what we normally do is to discretize the x coordinate into a number of divisions. Call them x1, x2, x3 and all that. So x1, x2, ... And at each value of x, we find the value of the function. And this is what we ultimately write out. So this is what we do, no? So effectively the function, when you want to write it, we write in terms of the value of the function at different positions of the x coordinate. And these are a finite number of divisions, and that's how we write it. So this can be expressed as a matrix, a vector, column vector. If say if it's some in this function, so f n at x1, f n at x2, f n at n. So this is a simple way of writing out the function. Now it is column vectors, right? And therefore we are able to write a continuous function in terms of column vector by discretizing the x coordinate. So in this case, what are the basis vectors? The basis vectors are essentially x1, x2, x3 and all that. So the basis vectors are the vectors xi, which is it is essentially like these are also columns. So 0, 0, 0, somewhere it is 1, 0, 0, 0, and this is the ith position. So this is how the columns, this is how the basis vectors are defined, and on these can be defined, right? So you can easily see that a function like the psi function can be defined on a basis like this, and in that case this basis will be these, and what are the demands on the basis? A, that they have to be orthogonal. So basis have to be orthogonal. With what does it mean? It means xi, xj has to be delta I j. Okay, that's one requirement. The other requirement is completeness. So the other requirement is completeness, which is essentially saying that the summation over I is equal to 1 to n xi, this should be equal to the identity operator. So these two are the essential requirements on the basis vectors, and we have defined the basis vectors as these, right? As like this, expressed as column vectors like this. So the ith position, it is 1. So the for the first one, it is the first position that will be 1. For the second one, the second position will be 1, so on and so forth. These are the basis vectors. And on that basis vector, we are expressing this, essentially saying that Fn at x1 times the first one plus Fn x2 times x2. So essentially, we are saying that each one has a weightage, and weightage depends on the value of the function at that particular location. All right. And then how do you define the inner product of two functions? The inner product will be, okay, before I go to the inner product, let me write how the function would then be written, and then it will be easier to write the inner product. The function will have to be then written as, Fn will be written as, essentially, n is equal to 1 to, sorry, not n, I is equal to 1. I is equal to 1 to n. It will be Fn evaluated at xi times the vector, the basis vector xi. Okay, this is how we are expressing then the function as a column vector. And suppose we have one function like this, another function like that. Say, let me draw another function, say something like this. This also is expressed as these positions, and then we are trying to write the inner product. So inner product this is what we are trying to write. Then that would be expressed as I is equal to 1 to n. Inner product will be expressed as Fn. It will be evaluated at xi, then Gn evaluated at xi. Okay. Well, this is for the situation where f and g are drawable like this. That means these are all real valued functions. If they are not real valued functions, we'll have to put a star here. That's all. Okay. Now, let us come to the moot question that I'm trying to drive at. That is, what will be our f? The magnitude of f? Magnitude of f will be ni is equal to 1 to n. Now, this is Fn xi, its square. Now notice the problem. The problem is that this number, this should signify the magnitude of the function, and that should not blow off. But here I have a number of these, and the more you increase the number of divisions, that means you make smaller and smaller divisions, this number will blow off. Right? this number will tend to blow off. That's one problem we need to encounter. And the way we normally you'll find in books that this is encountered is that we define Fn Gn as it is n equal to, sorry, I equal to, mistake again and again. I is equal to 1 to n. Fn xi gn xi. But now we have to multiply with something so that it does not blow off. And what is normally done is to multiply by L is the total length that you are integrating over, and n is the number of divisions that you have made. And then this will not blow off, and we can have a definite value of this function. You can have a definite value of this also. Okay. So it remains bounded. It remains bounded. And if it remains bounded, then we can write it in the limit, g, sorry, not n, because now we are taking the limit. It will be integral 0 to L fx gx dx. In order to do that, and for complex functions, for if f and g are complex, then you have to put a star here. Yeah. So we define in case of the continuous basis vectors, we define in a particular way so that in the limit we can get this back. This is what we actually want to achieve. That's what we want to get back. Now the question is still, a question remains regarding the character of the basis vectors. How are they normalized? So how are the basis vectors normalized? Orthogonalities, so for example, x and x that are supposed to basis vectors. Then orthogonality will demand x dash equal to 0. Delta ij, so this will be equal to 0 if x is not equal to x prime. That is understandable because you see the way we have drawn the picture, sorry. The way we have drawn the picture, x1 and x2, if x1 has a value, x2 does not have a value, and therefore this is understandable that will happen, that this will be, if they are not equal, then it will be 0. But will this be true? Will that be true? Now, you'll see that there is a problem with that. We cannot have that. In order to understand this, let us do it the right way. Then you will understand what is the problem with this. So we know that the x prime k, this is the projection operator, summed over k should be identity operator. This is something we learned. This implies that if you sum over all the values of k, this implies that integral a to b and make it I mean, in the limit, it will become integral from a to b, x prime dx prime should be equal to the identity matrix. Okay. That means this is something that we learned earlier. All we have done is to say that we are dividing into infinite number of such small elements, so that at the end it converges to an integral. Therefore, the integral has to be the identity. Now operate with the bra x to the left, and any function, say f, with the right. So what does it lead to? It leads to integral from a to b. This first x, then I have this x prime, and then we have x prime, and then f here, dx prime. Should be, here it was I, therefore we operate with x in the left side, I, and f in the right side. Now I operating on f is nothing but f, therefore we can write it as x f. Okay, now what is this? This is projection of f on the point x. So this is nothing but the value of the function evaluated at x. So this is nothing but the f x, f evaluated at x. Okay. Now we do not know what this is. This is what we are trying to find out. We try to find out what this should be. Okay, should that be 1? That's what our question was. So let us assume that to be some function. Say, let x prime, here it is, be some function of x and x prime. Say a function delta of x and x prime. So this is some function of x and x prime. We don't know yet what this function is, but we are just writing it as this function. So this then becomes integral. Now we can change the limits because we are talking about two values of x that are close to each other, and there is nothing that is happening outside that range, and therefore we can, for all practical purposes, change the limit to x minus epsilon to x plus epsilon, because nothing beyond that happens. Everything is 0. So we change the limit, and then we can write this one. This is actually we are written as delta x prime, and then we have this, which is f evaluated at x prime, right? So this is nothing, right, so that you don't get confused. F evaluated at x prime, otherwise it might look as inside the integral, then dx prime. Now what is this? X and x prime are two close quantities, and it has to be such that it results in fx. which means, this essentially means that this quantity x minus epsilon and x defined as delta x prime dx prime should be equal to 1. Now, this is the demand over whatever we define as where was it? Yeah, as this the inner product of x and x prime. So inner product of x and x prime should not be actually 1, but actually should be such that its integral over a range equals 1. So that is the character of the delta function, Dirac delta function. So this is the delta function. So in order to understand what the delta function actually is, there are a few ways of trying to understand that. One possible way is to simply say that, okay, let me erase some part upstairs and then it will be easier to write.
Sir, may I interrupt you once?
Sure. Was it?
Sir, yeah. So, sir, could you go back to the presentation once where you, so could you go down a little below, so towards the end?
Yes. Where exactly you asked me to stop?
Okay, here. So how did you take f of x dashed out of the integral? Because like we are integrating over dx dash, right? So how can we take it out of the integral?
Oh, well, okay. Let me clarify this. Here is a function. Good. That's a good question that has come. I appreciate that. We have two very close positions, x and x dashed. The value evaluated at x is fx, and value evaluated at x dashed is fx dashed. So this is f of x, and this is f of x dashed. Now, if these two numbers are very close to each other, then fx and fx dash should be very close to each other. So for all practical purposes, we can say that fx dash is actually fx, and thus what we said is that this is f evaluated x prime. So we had to write it here, but then we said a bit of mistake here. There, this should be actually fx. Yeah. We wrote that it is, for all practical purposes, this can be seen as almost equal to fx, and therefore we took it out of this and then integrated this in delta in terms of x prime. Okay, so the way we took it out is to say that it can, for all practical purposes, be said to be the same as fx rather than fx prime. So we can take it out, leaving the rest, and then the rest has to be 1, because the right hand side has to be fx.
Okay, sir, got it.
Got it? Yeah. All right. So before we end, I'll just clear up this part and I'll give you a sense of what the Dirac delta function actually looks like, or how it can be visualized. One good way of visualizing that is to assume or I'd better use this one. Oh, sorry, I'm not used to this. Now, suppose I have got a function looking like this, and this is a this say is omega, and this say is 1 by omega. This height is 1 by omega. So that the product is 1. And now you make the omega slowly go down so that this becomes narrower and narrower. And as it becomes narrower and narrower, the height goes larger and larger. Okay. And still, all that happens keeping the area same, equal to 1. And that's exactly what we demanded here, right? What we demanded here was that the area has to be 1. So the character of the delta function is essentially such that its integral over a certain range, epsilon, should be 1. But, well, here we try to figure out whether the x prime should be 1 or not. It cannot be 1. X prime should be, or should be delta. It should be such, this number should be such that whose value, if integrated over a certain range, should give 1. But the value itself can go to infinity. Now, in this sense, this particular function differs from the kind of functions that we have defined in our function space. In our function space, we said that the function space consists of those functions that are normalizable in the sense that nothing, it doesn't go to infinity at any point, right? But this does go to infinity at some point. And yet, it ensures that the area under it remains 1. And that is the demand on this. Now, it is time to define what is the Hilbert space. The Hilbert space is where the elements of the Hilbert space are the ones that we earlier defined as the function space, namely the normalizable functions, but also is normalizable functions, normal normalizable size, plus those which can be normalized into Dirac delta functions. So in that sense, we need to additionally consider this, because the eigenfunctions in the continuous space would be of that character. So they have to be normalizable into Dirac delta functions, but they might have infinite value at those points. So the character that we demand is that their area integrated over a range, small range, should be 1. Okay, so all the functions that we'll deal with are elements of the Hilbert space. Okay, so far we have talked about the normalizable functions, but the moment we have to come into continuous basis, we have to deal with this particular issue, and therefore we needed to expand the definition, and that's what we did. Another way to visualize the Dirac delta function is to consider the Gaussian. This Gaussian function is delta x minus x prime is equal to 1 by root pi delta e to the power minus x prime square by delta square. This is a function which is this is something centered at equal to x. It has width delta, height 1 by root pi delta, and unit area. Now imagine that you are slowly reducing delta, and delta tending to 0, delta tending to 0. Then what happens? What happens is that its width becomes narrower and narrower, height becomes taller and taller, and at the end it becomes the delta function that we defined. So delta function can be defined, imagined this way. Delta function can be imagined like a Gaussian. So it is essentially something like this. But slowly it's becoming narrower and finally becoming something like this. And at the end, it becomes a delta function. So there are various ways of visualizing a delta function, but essentially the point is it is something which has 0 width, but it has a finite and unity area. That's important to understand.
Sir, I have a question.
Yes, Sharon, yes.
Sir, in the particle in a box problem and similar problems, we have seen that the momentum basis is actually discretized. I mean, it takes discrete values.
Momentum.
Okay. Yes.
Momentum.
Yes.
No, the energy gets discrete values. Momentum does not.
But sir, the momentum basis has.
No. Here also we discretize the position basis, right? See,
Yes.
when you talk about basis, we discretize the x coordinate, right? That way we could define it. That's something that we are imposing. Nature does not impose any discretization. But in energy, nature imposes a discretization. That's the difference. Here also we have discretized the x coordinate, saying that one point is called x, another point is called x prime, or x1, x2, x3, x2, x4, and all that. We have done all that. No, I erased, I suppose. Yeah, I erased. So we have defined that way. So that is also a discretization of the x coordinate, position coordinate. But position itself is not a discrete variable. Position is a continuous variable. We are doing it so that we can, at the end of the day, express operators, functions as matrices. And we are discretizing in a finite number of discrete segments so that we can ultimately define a matrix of that dimension. That's what we are essentially trying to do. The vector that will define psi as a vector in position space, position basis, will become a vertical, a column vector of how many numbers? That many numbers into which I have divided the x coordinate. In a similar way, we can do for the momentum also, but that is not an inherent discretization. It's something that we are doing it in order to make our calculation simpler. Okay, momentum is not inherently discretized in harmonic oscillator or the infinite square well. It can take any value.
But sir, in the infinite square well, we can expand any wave function in terms of Fourier series, right?
Yes.
And each term in the Fourier series, if we take e to the power ikx and minus ikx, those are momentum eigenfunctions.
Yeah, k is continuous variable.
But sir, the barrier we put at the end makes k discrete.
That's the extremity. That's the extremity. In case of the infinite square well, there are extremities. In case of the harmonic oscillator, there are no extremities, truly.
Yes, sir. I'm talking about the infinite square well only.
Yeah, infinite square well, you do put extremities, but the number of k still remains a continuous variable. K within those extremities does remain a continuous variable. So it does not have a discrete values. It's only for the sake of our calculation we take discrete values to calculate the Fourier transform. But it's actually an integral with continuous values. Okay, so k is a continuous variable.
Okay.
Yeah, we will deal with how to express things in momentum basis. We'll do that.